A big thank you to all of our colleagues that invited us to present at the Vanadium Flow Battery Forum. I'm excited today to talk about our work that we've done in close collaboration with Vanatech on carbon accounting of vanadium flow batteries and on how much of a difference vanadium flow batteries are making on the energy transition, as well as to think a bit deeply about the supply chain issues associated with vanadium flow batteries. So vanadium is an incredible transition metal. It has incredible versatility in its reactivity, in its redox, which makes it a hugely effective energy storage vector. Oxides of vanadium are finding use in lithium-ion battery cathodes. There are lithiated vanadium oxides that are being used as anodes in different sorts of lithium-ion battery configurations. And then, of course, we've got this incredible opportunity that lies with vanadium flow batteries to revolutionize what our electric grid looks like. But what's really urgently needed is to have benchmarked assessments of vanadium and other critical minerals that are needed for the energy transition so that we can expand access and figure out reliable supply chains for the future. So what I'm showing you here is a timeline that Ben Rogers in my group at Texas A&M has put together that shows the sort of the advent of vanadium flow batteries from its first discovery at the University of New South Wales through initial prototypes, initial first commercial products, to these large, exciting batteries that really are now seeking to reimagine our power grids. And we're hearing news of ever larger form factors coming online in China. The top half of the slide sort of juxtaposes information on recent supply chain challenges and opportunities that we've seen. And I think the juxtaposition of these two really brings into view the importance of having reliable and resilient supply chains. So we're going to need a lot of large vanadium flow batteries to power the energy transition. This is a critical piece of technology. It's a critical gap to the energy transition, but this will require access to critical materials. And this is the theme of my talk. We're going to need to work together to ensure access to critical materials. So continuing with the same theme, this is a rather data-rich slide. And on the one hand here, we're showing current vanadium consumption dominated primarily in the past by the steel industry, but increasingly we're seeing vanadium flow batteries account for more and more vanadium consumption. This number is going to grow very steeply in the years to come as vanadium flow batteries come online. And this has led to some worries about there being an emergent production consumption gap. What I'm going to try to do in the first part of my talk is to quantify the benefits of vanadium in the form of carbon and energy savings in major sectors. Vanadium finds application in many different areas of industry. One major set of applications is, of course, in construction, in rebar, in steel sections, in automotive steels, and then in vanadium flow batteries. I'm going to focus primarily on vanadium flow batteries today, but I just wanted to put up a list of our publications that provide, over the years, we've come up with a pretty comprehensive assessment of carbon and energy savings derived from use of vanadium. And this is an ongoing project, so look out for more publications in the years to come. So as a quick overview of construction and how much energy and carbon is saved by using vanadium alloyed steel, I think it's important to remember that the biggest impact on carbon footprint and embodied energy comes from the actual materials that are used in construction rather than the use phase of a building. So the choice of materials determines really how carbon intensive, how energy intensive a structure is. This is our overarching framework for doing life cycle assessment. What we've tried to do is to figure out how much material savings accrue from using vanadium microalloyed steel. So how little steel we can get away with to get the same structural properties when we use microalloyed steel, which have better structural properties as compared to conventional rebar. And from there, we can figure out in terms of how much material savings there are. We can figure out the embodied energy and the embodied carbon savings. And then we can scale this to a building model and figure out how much energy and carbon is being saved through the microalloying process. I'm going to skip through some of the details that are in the paper, but essentially what we've shown through structural modeling is that there's as much as 61.06% savings in how much material is needed when we use 500 megapascal steel in reinforced concrete beam as compared to 250 megapascal steel. And this then results in massive reductions in carbon emissions for the same building because of how much less steel we need to make that building. This all adds up. Our life cycle assessment work suggests that vanadium microalloying results in very large savings of carbon across the world, especially in China, where reinforced concrete structures have become quite common, and where microalloyed vanadium steel rebars are finding increasing use. And just to keep in mind, it's not just embodied carbon, but also massive embodied energy savings that accrue from using microalloyed steel. These are some really large numbers. So to put some of these big numbers in perspective, 136 megatons of carbon dioxide translates to the avoided emissions from 30 million passenger cars driven for an entire year, or from the savings that would come from not burning 300 million barrels of oil, or from 30,000 wind turbines running for an entire year. So these are really spectacular large numbers that come from using vanadium in the construction industry. Now, turning our attention to energy storage, we live in a really exciting time. We're seeing a whole host of battery chemistries come to market, spanning a vast range of capacities, different durations, and we're going to see battery storage capacities containing vanadium probably in many aspects of this map, all the way from intraday energy storage, where you're going to see some lithium-ion batteries, perhaps some interesting aqueous chemistries, as well as for much longer durations where vanadium flow batteries really start to shine. So the question we set out to answer is, are the net savings from installing a vanadium flow battery still positive after accounting for its carbon footprint? And this is particularly relevant to renewable energy, to wind farms, to large solar farms, where oftentimes there is no energy storage whatsoever. When there's the wind is blowing and the sun is shining, there's oftentimes massive curtailment that has to happen, squandering some of the energy that we could have used in the grid. The other question we wanted to ask is, how do vanadium flow batteries compare with lithium-ion batteries in the context of coupling to renewable energy sources? So here are some key assumptions that go into our analysis. We're comparing a vanadium flow battery from its production, the cost of the vanadium electrolyte, the carbon and energy costs of the stack components, and then through its use phase to end of life, and at least one recycling step. And we're contrasting it to a conventional lithium-ion battery that has a LFP cathode and a lithium titanate anode. A couple of key distinctions that pop up right at the beginning, of course, vanadium flow batteries often have a much longer lifetime. And once they're done, you can really get a tremendous amount of value out of it because the electrolyte can be readily recycled. And we've accounted for one recycling step after 20 years, but there's increasing evidence that you can keep using the vanadium electrolyte, keep recovering it, and it really is an asset that is conserved in the battery. We're assuming a nominal capacity of 8.3 megawatt hours in doing this comparison. The one place where you see that VFBs don't do quite as well as lithium-ion batteries is in terms of the round-trip efficiency, right? So 75% as compared to 90%. Again, this is a bit of a moving target, but this does show that especially when you're not linked to to renewable energy sources, some amount of energy is being squandered because of the low round-trip efficiency. We're assuming vanadium extraction based on co-production with steel. This is also a moving target. There's many more highly decarbonized, low carbon vanadium coming on the market, and this is going to change some of these numbers. I think this is an exciting time to be in vanadium right now. And we're assuming electricity from wind turbines, a photovoltaic installation, or an average grid mix. So these are some of the initial figures. So as you can see here, especially for renewable energy sources such as wind and solar, vanadium flow batteries do really well in terms of having a lower carbon footprint as compared to lithium-ion batteries. Again, because of the lower round-trip efficiencies, some of this advantage is lost as you go to more conventional grid mixes. But of course, the entire purpose of having a battery integrated in the grid is to couple to renewable energy sources, right? So in the areas that matter, vanadium flow batteries do really, really well. If savings from recycled materials are not considered, just considering a cradle to gate scenario, VFBs generate 30% less CO2 than lithium-ion battery for every 1 megawatt hour of capacity. If you do consider one recycling step, then this advantage gets further amplified, 78% less carbon as compared to lithium-ion battery. And really, I think what we've seen in recent years is this tremendous growth in recycling of vanadium flow batteries. And it's clear that we're going to be able to recycle these many and many times, and that there's going to be amazing residual value that is inherent in the vanadium flow battery. Considering the entire life cycle, vanadium flow batteries do have some disadvantages as compared to lithium-ion batteries. I've talked about the lower nominal energy density as well as the lower charge-discharge efficiency. And the impact of these inefficiencies gets amplified if you're not connected to a clean energy source such as wind and PV. But of course, the entire purpose of having a large grid integrated battery is to help with reducing curtailment of green energy sources. So you do see in the situations where you're coupled to wind or PV, VFB generates a lot less CO2 as compared to lithium-ion batteries. How much better? Well, so if coupled to a wind source, currently operational VFBs are projected to save 2.13 million metric tons of CO2 over the 20-year lifetime. And this is a number that I want to emphasize is rapidly increasing as we see these massive projects start to come online, particularly in Asia. So this is, again, a rather conservative plot showing currently operational, under repair, under construction, and announced VFBs. And again, this is a rapidly moving target because we're seeing these huge projects getting announced and really very rapidly commissioned. But here are some numbers in terms of how much CO2 is saved for curtailment scenarios. So comparing to a situation where there's no energy storage option whatsoever, as well as comparative scenarios comparing to lithium-ion battery as an alternative. So we're really getting some really large savings already, and these numbers are going to exponentially increase as we see larger batteries coming online. So where do we go from here? I think there's a lot of interesting directions that this is headed. On the one hand, uh, this is the baseline scenarios that I plotted that I've shown you before. On the one hand, we're seeing increasing efficiencies of vanadium flow batteries. This is coming from the design of the stack and from sort of technological advancements in the configuration of the battery. And this is going to push up this number, this round trip efficiency number, quite a bit. And we're also starting to see much cleaner processes for extracting vanadium and also more rigorous accounting. And this is also going to reduce the carbon intensity of vanadium production. And so we're poised to see even better numbers in terms of carbon costs for vanadium flow batteries, coupled to wind and solar here as examples in the years to come. So looking to the future, we're seeing this massive projected demand for vanadium in the context of vanadium flow batteries. Many of you have seen the Guidehouse report and projections for capacity of vanadium flow batteries, especially in Asia. Early days yet, but we're starting to see some of these predictions come true or even be exceeded in certain parts of the world. And what we've done is taken these predictions and said, well, look, if we had all this total capacity, we've calculated two separate scenarios, the avoided curtailment, comparing where you've got wind and solar or wind alone, and you're comparing this to there being no energy storage whatsoever, or the comparative scenario where we're comparing it to there being lithium-ion battery alternative. And we see that these carbon savings are just really large, comparable to what millions and millions of acres of US forests would have been able to do. So these numbers do start to add up, especially as the projects become supersized, as these projects come online across the world. The message I want to leave you is that vanadium flow batteries are continuously improving. There's worldwide research going on that is attempting to increase the energy density, the round trip efficiency, working through issues with electrolyte conductivity, electrolyte concentration, and the stack configuration. And then on the other hand, we're seeing access to vanadium electrolyte from a wide variety of sources, primary sources, secondary sources, and there's a lot of active efforts amongst Vanatech members to reduce carbon costs of vanadium extraction. And both of these together will further push the carbon and energy benefits of vanadium flow batteries and make it much more competitive with other alternatives in the years to come. Okay, so let me go back to this question that I posed at the beginning of the talk. We've got this massive expected demand in vanadium flow batteries. Where is this vanadium going to come from? So let's think about this a little bit more deeply. What we've started to do is working with our colleagues at Vanatech and with Vanatech members from across the world is to come up with the set of databases, interlinked databases that capture the entire world of vanadium, from production sites, primary, secondary, every sort of production site that we can document, actual processing facilities of different types, as well as actual vanadium flow battery installations. And what we're trying to do is to keep a real-time map of where you have material available, where vanadium is getting processed, and where batteries are getting installed, and how they're doing over the years. This map here is our first attempt to start putting together this world of vanadium. It captures all of the different deposits of vanadium, some of which are being actively mined, some of which could be mined in the future. It plots major VFB installations. It gives you an idea of how VFB capacity is distributed across the world, and the different types of vanadium production going on. So we're hoping that this is a snapshot, and through capturing this at different points of time, we're going to be able to see how our ecosystem is evolving as vanadium flow batteries become a key instrument of the energy transition. You can start to view these maps now on Vanatech's website. This is an example that I think really nicely shows the enormous spread of large VFB installations across China. We would love to get any information that you might have that we might be missing. We're not claiming to be comprehensive at all, and we absolutely need your help. So if there's anything that you see that's missing in the map, please do send us a note, and we'd be very happy to add this in. So as I also mentioned, we're seeing vanadium being sourced from many different types of deposits, primary, secondary production processes coming online. And I think we're realizing that there's oftentimes not been a rigorous accounting of CO2 emissions associated with vanadium production. And we're starting to build out an interactive carbon emissions calculator that will start to account for every one of these different aspects and come up with reliable benchmark numbers for different V2O5 product or ferrovanadium or electrolyte. And I think that's going to give folks the opportunity to make informed decisions. One of the key aspects we're interested in figuring out is what are the CO2 emissions associated with vanadium production. There's multiple numbers out there. And so what we're also trying to do is to benchmark these and get some reliable estimates. And as you can start to see, in many cases, these numbers are actually a lot lower than what has been reported in literature. And so I think the outlook is really promising in terms of decarbonization of vanadium production. There's a lot of excitement now about how we could really make this green metal a low carbon metal in terms of how it is sourced. As part of this same project, we're trying to get a good assessment of how much energy and carbon is consumed in processing vanadium, again, both in primary production or secondary production, from spent catalyst to fly ash and so on and so forth. And if you have any suggestions whatsoever, or any numbers that you think that you might be able to provide, or better process flow diagrams than what I'm showing here, we would welcome your suggestions. Please send us an email, and we're happy to chat more. So to conclude this part of my talk, I hope that I've been able to convey the excitement of VFBs at this moment in time. VFBs are really critical to avoiding curtailment of solar and wind, and they're really going to be a huge instrument to entirely reimagine the way that our power grids work and to amplify the emissions reductions that are possible through adoption of clean energy. And what I've shown you is the VFBs have a lower carbon footprint as compared to lithium-ion batteries when coupled to wind and solar. And this number becomes even more significant considering that many parts of VFBs, and certainly the electrolyte, can be recycled not just once but multiple times. And again, we're in an exciting moment in time where carbon savings are sort of increasing as technological advancements drive improvements in efficiency, as we're in this new age of decarbonized vanadium production, and there's better recycling of stack and electrolyte components. One of the things we've tried to do is really think through very deeply about where vanadium will come from, that we need to make these large batteries and to feed the substantial growing demand for VFBs, and this World of Vanadium Living database that we're working on in collaboration with Vanatech is a really good way to track reserves, production, electrolyte processing, and so on and so forth. But we do need input from all of you, so please do send us any information that you might have that you don't see on Vanatech's website. And we're hoping also to keep working on this carbon calculator to capture the entire workflow from vanadium extraction to battery use case. And I think this is going to be an effective tool, a useful tool for the entire industry. So I want to take a few moments to discuss Vanatech's role in this. We're very grateful to Vanatech for having funded this work, for bringing industry together to expand markets, to promote a stronger vanadium industry. I think we're all in this together. And one of the fun parts of this is this new visual identity, the vanadium flow battery and this logo, and I think it symbolizes recyclability, reusability, longevity, low carbon footprint, and the fact that we've got an integrated industry, an integrated, reliable, sustainable, low carbon supply chain that is available to bring about, to amplify, to empower the energy transition.
A new era of energy storage is here, unlocking a sustainable future. The vanadium flow battery, from capturing energy to capturing attention, with a powerful new icon. A symbol representing recyclability, reusability, longevity, low carbon footprints, and a unified industry. Vanadium flow batteries are trusted for their unmatched durability and scalability, and as a 50-plus year asset, are suitable for a wide range of applications, from small commercial buildings to large-scale grid integration. Vanadium flow battery deployments are growing, predicted to experience a 22-fold increase. And due to vanadium's role in clean energy technologies, the World Bank predicts a near 200% increase in vanadium demand by 2050. The use of this icon is an assurance of quality and of a commitment to the vanadium industry and our sustainable future. Visit our website for an interactive map of existing installations, fact sheets and animations, press releases, research papers, and more. Let's build a cleaner world, one powerful battery at a time.
So please reach out to you, Lee, if you would like to have your logo on the Vanatech website. Thank you again for the opportunity to come present to you, and I hope that next time we'll be able to meet in person. Thank you.